that I wanted to say that I asked before. So like one question was, do you think we can exploit in the variable set, in the discrete log setting, if we can exploit a structure referencing for functionality? And well, I think it's a nice thing to, it's a nice formal argument to make that I think this would not be possible, because if you think about it, in the discrete log case, an adversary cannot even distinguish if the key is structured or is not structured. Okay, so there's like, seems like a very high evidence that actually it's not really possible to exploit this way. The final thing I want to say is, because some people ask me, is like, I didn't say anything about references. I didn't do any of this work. So here you have the basic references, and this trick with amortization essentially comes from this paper of this notion of accumulation, comes of this paper of Bo and Hubbook, the Hubbook, which is Halo, which is also one of the SNARKs deployed in practice in the discrete. Another interesting things, last one, is that actually I think this is also a very interesting paper to think about. I'm happy to discuss this in the break, because this paper relates the sum check protocol in certain sense to bulletproofs. Okay, so since we saw with Jonathan, we saw the sum check protocol, maybe it's like good to unify things. Okay, so it can be seen that bulletproofs is sort of like a special case. Although, of course, usually when we think of the sum check protocol, we're thinking of interactive proofs, we're thinking of things that maybe are information theoretically. So, but you can do a certain translation. Also, you're checking. So that's it. Now. Okay. So this will be more of a hand waving presentation. Sorry. Okay. So first thing is, like in the previous talk, I didn't really talk about SNARKs. I just said short proofs in general. So like the first thing that is like due is to define what is a SNARK and what do we use them for. And I actually think that the best, you have the classical zero knowledge proof presentations to people trying to solve a Sudoku and so on. But I think right now, the way people think of SNARKs is really like as a proof of computational integrity, right? This is a term invented by, I think, Starks, like the Levanzas and so on. So essentially, we're using the setting in which we're thinking of using SNARKs is the following. We have a big computation. It has a public input, possibly a public input, maybe a private input, and at the end of the day, we want to make sure that this computation is correctly executed, okay? And this is usually we think of this as an arbitrary computation, typically quite big. And then what we have is like a zero knowledge proof that this computation has been executed correctly, and we say zero knowledge, and people say zero knowledge when often it's not zero knowledge, okay? So people are using zero knowledge all the time, but actually they mean just a proof. Because in this setting, the property we often care more is just the integrity property. Okay? We care more about the fact that this shows that this computation has been executed correctly, and only occasionally we care about privacy. What is a zero knowledge SNARK? Well, is very roughly is anything where this proof that the verifier accepts as result is really shorter than the input to the computation, to the side. Okay, so how are SNARKs built? Starting with this effort, the ZK proof standardization effort, people try to like come up with like somehow standard notation. But of course, everybody has their own way of thinking about it. But usually, like the recommendation was to distinguish between front end and back end. Okay, so what is the front end? So it's like really what the user who wants to do a zero knowledge proof, well, he's thinking of, he has a computation and he wants to prove it. Okay, so what do we need to do? when we want to do a SNARK. So first we get a computation, and we actually need to transform it into something that is amenable for creating zero knowledge proofs. Okay, so which means that usually we transform whatever our program is into a model with some restricted operations. Okay, so it can be the typical model that we use is arithmetic circuit, but you can have like more expressive models. So let's say I have an arithmetic circuit with lookups, or you can give it additional powers. And from this model with restricted operations, I always like to think about it as transforming into a set of algebraic relations. So this matrix has this times this other vector is equal to something else. So like there's a set of algebraic relations. And then the whole point of SNARKs is to translate this into polynomial relations. It's debatable if all this is really like front end is really what the user sees, but I like to put it here because for now, really, we haven't done anything. Okay, there's like, it's just ways of rewriting the computation often. Okay, there's like ways to, in the polynomial relations in which really we have to do a lot of work, but often there's like an automatic way to translate algebraic relations into polynomial relations. So all these are, we have a computation, we rewrite it in a way because later we want to do zero knowledge. Okay, and then what happens when we have written this computation is that now come the cryptographers and they create a proof for that, and they deliver this this proof. And this is usually also defined in two steps. Okay, first people think of a protocol that's information theoretically secure, where people exchange as polynomials. So prover of sometimes there's like a few preprocessed polynomials. So this sometimes then it's like a preprocessing polynomial interactive oracle. So they have like some common parameters. And then they exchange messages, they exchange polynomials. This can be multivariate or univariate. And then from this, we have a SNARK. And in this step of transforming the preprocessing polynomial IOP to a SNARK is where cryptography comes in. Okay, so here we have a polynomial commitment, which is the thing that will give us succinctness. Okay, so until here, everything is information theoretically, no compression. These are large messages and so on. And at this point where we add the polynomial commitment and the cryptography, it's where we start having like these trusted parameters, okay? That's like the common reference string. I distinguish between the structure reference string or common reference string, which could be like transparent, it can be anything. Okay, and what's the key idea for transforming this polynomial IOP into a SNARK? Well, the main idea is that all these polynomial relations that we are checking, that the prover and verifier are sending and checking each other's will be checked at a random point. And this is the key point to succinctness, right? So we have, so here we have done nothing except rewriting the computation and finding a way of describing a protocol where parties send each other large polynomials. And here it's easy to have like unconditional soundness. But at the moment where we compress, we need some security, and this comes from the fact that the polynomial commitment tells us that these polynomials that we send here open correctly at a certain point. And then we can check. It's essentially randomized polynomial identity checking, okay? That gives us the security. I won't talk again much about zero knowledge because this comes almost for free in many cases, right? Because you have like things that are so compressing, okay, that they almost leak no information about the secret inputs of the computation. That's the idea. So how do we think of like the state of the art and what we need to do for SNARKs? Well, often the scenario where we have is that we start with a large computation, then we write the computation in a restricted model, and then we already have a blow up there, right? Because we originally wanted to do more operations and we have to write it in a way where the model is more restricted, and here means this is even larger. So what does it mean? That in reality, we're proving things about very long vectors. We have very large degree polynomials in reality. And then these end up really being a lot of work for a proof, okay? Especially in the setting we're discussing today, which is the setting of many practical SNARKs, in which the prover is doing all these as like a group public key operations. Also, there are operations in a group where the discrete logarithm is hard. It's very expensive, even with Pfeffinger and everything, right? Okay, so a typical example of computation is we have like a circuit we want to prove. It has 2 to the 20 multiplication gates. And
I remind you of the pointer. I don't know whether it helps.
I think I need to move.
It's against the other part of your culture.
Okay. Okay, so an example would be C is a circuit that has 2 to the 20 multiplication gates and is defined over a finite field that has 255 bits, which is like the scalar field of some elliptic, for instance. And that's not even very large. Okay, we want this circuit to be bigger and as big as it can be. So which means that all the scaling problem, we have all the scaling problems you can imagine, because actually there's no limit to how much you want to scale these things. Okay, so what is a good SNARK? So zero knowledge proofs, you can do lots of research in zero knowledge proofs because you have so many trade-offs, right? That you can always like change one thing for the other. So one thing you can try to optimize for prover complexity and for verifier complexity. My point here, this is why I highlighted both parameters, is that around 2016 with or like the first NARCs, there was a strong focus on verifier complexity. Everybody wanted to get the shortest possible key. So as we will see today, Growth 16 has like a very, very short proof. But now there's like a lot more effort on improving the prover complexity because of this idea that we really want to scale this like massively. Same thing for proof size. It's no longer so important as it used to be. Okay, so we are happy to trade a bit of proof size for maybe better performance for the public. Obviously, we're all the time caring about public verification. Another parameter is this trade-off between transparent setup and structured reference string. Personally, I don't care about structured reference, so about using structured reference string. I think we make very wild assumptions, so I don't think that's like the wildest of all assumptions. Anyway, so what will I talk about this talk? So in this talk, I will talk about some SNARKs that typically have what is called a quasi-linear prover. Okay, so which means that if the circuit has n multiplication gates, so the running time is n log n, the proof size is constant, and I either have usually like sort of constant size verification, or sometimes you can allow for logarithmic number of field operations. So these are typically what's called preprocessing univariate PIOP, okay? Looking ahead, why do we say preprocessing univariate PIOP? Well, we need preprocessing because like the verifier is trying to verify a statement, right? It needs to read. So it has to read the statement, or has, then it's like linear because reading it has to read the description of the circuit, right? So in some sense, we can only hope, so not in some sense, like we can only hope to have constant size verification if someone is reading the circuit for the verifier. So if somebody is like processing it for him. And these type of commitment of SNARKs are the ones that you can build from KZZ, Kates-Baruch, Goldberg, polynomial commitment schemes in pairing groups. I will not say anything about this because this is Arantxa's domain. She will tell you how to everything you need to know, and never dare to ask about the KZG polynomial commitment. This is the focus of this talk. but recently you have to know there's like, as I said, a lot of effort in improving the prover. So there's like a lot of interest in provers that are linear. So the people call these like time optimal provers in some sense, because like you cannot really do better than linear in the size of the computation. And these ones typically have log n proof size and log n, at least log n verification, maybe polylog verification. So, and usually these are preprocessing multivariate PIOPs. What's behind the machinery that is behind is usually the sum check protocol that Jonathan explained. Okay, so one thing I didn't tell you in the previous talk is I show you how to prove an inner product relation, but I never told you why you want to do that. In fact, what we really want to prove are relations of this form. Okay, so we want to prove statements like this is the simple. As I said, there are like several. When we start with a computation, we always write it in a restricted model. So the simplest of this model is just have as computation. We rewrite it as a circuit. So I will assume my computation is a circuit and my statement is something like this. So I'm trying to tell you that there's like a secret input such that the circuit evaluated on public input 1, x1, x2, outputs x3. So x1, x2, x3 are public, and I'm trying to tell you there's like a witness that satisfies this, okay? So So this can be written as a circuit, and the interesting thing is that I put the multiplication gates in red because at the end of the day, when we will rewrite this relation, like this computation, as a set of algebraic relations, what really matters are the multiplication gates. And the idea is that everything that comes before of multiplication gates can be absorbed into the matrix. Okay, so we can write this. We can write this computation that the circuit. So the statement that we want to make that this evaluates to x3 as in this form. Okay, saying that there exists a Z, a witness Z said that this relation is satisfied. This is called a rank 1 CS relation. And the public inputs are correct. Okay, and you can see that, well, these are just the public inputs. Anyway, the point is that here you have that if the left gate is 2Z2, then here you will put a 2 in the matrix. If the right output is Z3 plus Z4, you put 2 ones here. So in some sense, all the additive gates and constants that come before a multiplicative gate get absorbed into the matrix, so that finally I have that my problem is of the size of the inputs plus the number of multiplicative gates. Okay, anyway, you can look this in more detail, but like the whole point is that I'm rewriting a computation, which is a circuit, as a problem called rank 1 CS, which depends on some matrices. The matrices are public and they are part of the circuit description. So if you know how the circuit is written, you know how the matrices are computed. And finally, what you have to know is that these matrices are very large. How large? Well, the size of the number of gates that you have, essentially. Okay? Okay, so the takeaway, and if I summarize what a rank 1 CS relation tells me, is that I have to prove 3 different things to prove a SNARK. First, I have to prove that the public inputs are correct. Okay, they are what they should be. Then you have to prove Hadamard relation, so you have to prove that a certain vector times another certain vector is equal to a third vector, and then you have to prove linear relation. So there exists a single value Z that is such that A, which are the left outputs, is equal to A times Z, B is B times Z, and Z is Z times Z. Okay? That's it, okay? The final thing to note is that these matrices are sparse. For me, it's always very useful when I'm thinking of proving R1CS, thinking I need to prove these three types of relation. Okay, so now the next thing I want to do is I have algebraic relations, I want to write them as polynomial relations, okay? So, and the thing is that not for all, but like for many of, so there are many relations for which this is like quite automatic, okay? So actually you don't need to do anything. There's no protocol like really involved. So it's like an isomorphism, no? If you have a vector, you can transform it to a polynomial. Here you're doing nothing. It's a change of basis, okay? So if I think of mapping a vector to a polynomial, then I can prove relations like a public input by just showing that if these two vectors agree on two positions, their polynomials must be divisible. So must be zero in all the positions in which they agree. So their difference must be divisible by the vanishing polynomial at the positions where we can. Okay. For instance, this is like maybe the most famous relation because it was used from the beginning. So let's say we want to prove that you have three vectors and they are in this Hadamard relation. Okay, how does this translate into polynomial? Well, notice that this, so you just have to show that A times B minus C is divisible by T of X, where T of X is the vanishing polynomial at this point. Why is this? I think maybe I'm going too fast, so let's take a minute to think why is this, okay? So when I map this vector to this polynomial, what I'm doing is interpolation, right? So this is the polynomial that takes the value y0 at R0, y1 at R1, and so on, right? So if I evaluate on any of these points R, this will be 0. Why? Because if I evaluate in R0, this will be A0, this will be B0, this will be C0. So this has to be 0 on all the points. So this has to be divisible by the vanishing polynomial at all. Okay? This is a bit more complicated. This theorem is called the univariate sum check. I will not show you how to prove it, okay? But what I want to show here is that notice that I just put one inner product here. Okay, I will come back here. So like I can prove, I can map, if I map vectors to polynomials, I can prove public inputs, I can prove Hadamard relation, and I can prove one inner product relation too, easily. So what I did, so let me emphasize again, I haven't done anything, but this is just a transformation. You map, okay, there's no cryptographic protocols, it's like a rewriting of things. And for any of these relations, given this transformation that I did, I immediately have a non-interactive PIOP. I don't know, let me show you an example, okay? So imagine I want to show that A, B, so that the Hadamard product of A and B is C. How do I turn this into a protocol? Well, the prover just sends A, B, and C, and H, and the verifier checks that A times B minus C is equal to H times T of X. Okay? So non-interactive, and so on. In fact, so this is the PIOP, the information theoretic part. How would this be compiled? Well, there are two ways of compiling it in some sense. Okay, so one is like what you do sort of in grade 16 because this is usually not called a compilation, but I think it can fall into the same sort of framework. And the idea is if in reality you would not be sending the polynomials, you would be sending the polynomials evaluated at a point in the elliptic curve, okay? And you want to check that and what you would do is check this divisibility relation just at one point in the elliptic curve. Note, yeah.
On the previous page, you said that the product of those polynomials needs to have roots at t, right? And there's a theorem that says that it's divisible by t then, right?
Yes, and this is what I'm using here, right? I'm checking that this is the case. So I'm checking this relation. I'm checking this relation. Okay. And how does what does the prover do to show that it's divisible? It sends the quotient. Okay. And this can be checked in two different ways. It can be checked with just in a completely non-interactive protocol. Okay. Because in reality, you're not sending the polynomials, you're sending the polynomials evaluated at the point, and you can check this with three pairings. Or you can check it in another way, which is like the more standard when people say we compile the protocol to a SNARK. Usually they think of using a polynomial commitment to verify this relation. Okay, so in this case, what you would be sending this point, you would be getting a random point, and then you would be verifying the relation at a random point. And also checking that the opening is correct, so that the points that the openings, the verifier send you are correct. Okay, so it's two different ways of doing a Hadamard relation.
The first is more efficient, right?
Yes, but it costs a lot of pairings. This is like, the first is what you do implicitly in Road 16.
Yeah,
right?
But for the KCG, you also need to do pairings, right?
Yes.
For the first one, you pay especially in the setup and what you need, the reference string on a CRS.
Well, in this case, no, because it's in Road 16, yes. But here, this is not a full R1CS relation protocol. I'm just showing how to prove Hadamard relation. So here there's actually, it's a good question in the sense that that's sort of my point, that this is a universal relation, the Hadamard. You do not need a specific setup to prove that. You see what I mean? So, okay. Okay, and the things that you need to compute this proof, so these are PIOP so this is the real protocol for proving Hadamard relation. What do you need? Well, the prover to compute all these values that it needs to send, which are the commitments to A, B, and C, it needs to know the powers of the trapdoor involved.
One question, how is this Z value chosen?
C?
The A of evaluated it, or is it a Z? Sorry.
I think it's
Oh, sorry, then it's tau. How is this tau?
Tau is a trapdoor, and it should be uniform to get security. Like at the end, it's like you, well,
Then this,
you have enough natural.
why should be some sort of setup?
Yes, part of the trusted setup. Like I didn't say that. Yeah, well, I said it here below.
Oh, yeah.
That's
Oh,
all right.
I see, sorry.
No, it's fine. Okay, so anyway, the point is you have a certain set of relations that are super easy to get a non-interactive protocol from, but not all relations. So not everything that we need for doing our 1CS proof is included here. Somebody sees maybe what is missing.
The linear operation, but maybe the inner product, would that be used for doing linear?
So the problem is that actually I need to prove not just one linear relation, but I need to prove many linear relations, right? I need to prove this actually corresponds to proving many inner products. For each row, it's an inner product, right? And how many rows do I have? As many as gates of the circuit. So this does not give me a way to do a succinct universal. So like a SNARK with only this setup. Okay. So
the bottom row there, you must have a typo, I guess, because a Z on the right, should that be sigma?
yes. Okay. Okay, so actually, this brings me to, so as I said, I think that results in SNARKs change a lot, okay? But the important thing is to focus on techniques. And I think that a nice way to classify SNARKs is to show how they go around this problem. The problem that we don't have a universal way to prove many linear relations. We know how to prove one, we know public input, but we don't know how to prove many linear relations, okay? So, and this is how we can, this is a way to classify constant size SNARKs. There are recently a few new SNARKs that I have to check also with constant proof size, but essentially this is like the 3 techniques that I know that you can use. The first one is for growth 16 that, as I announced, and you probably already know, it has the shortest proof size. And this one uses something called quasi-Nizic arguments. Then there is like a very popular proof system, which is called Plonk. And the idea is that what Plonk uses is a technique. So it needs a technique to prove linear relation, and the technique that it uses is a permutation-based argument, okay? So, and essentially, essentially the idea is that if M is a permutation matrix, you have like a big product that has to be equal in 2 sides, okay? This is a polynomial. In reality, it would be evaluated at the trapdoor, and 2 polynomials, you can show that randomizing enough, that's actually a simplification, that with some randomness, like you embed, you turn this into a randomized product, and the 2 sides of the product can only be equal if this is a permutation, okay? And then there is Marlin, which has another technique. It's usually called the lin check, that's used actually in many other protocols also, for instance, for code base. So like that's a common technique when you cannot do anything else. Lin check.
Or linear.
Yes, it's like the sum check plus something else that we call checkable space sampling in one paper, but I think, anyway, I will come back to this, okay? So I think this is like a way to think of SNARKs, because with these 3 different techniques, because you will see this gives you different performance, just thinking on how they do this strategy. Okay, so the first, let's go to growth 16. What is the technique that it uses for proving linear relations? And here I had like a bit of a maybe nostalgic moment, and I have to talk about quasi-Nizic arguments. I think people that were doing research in 2014, 15, like Benoit, Mark, so they talk about quasi-Nizic arguments, but people don't usually refer this as a quasi-Nizic, but it is, okay? But I thought this is a workshop in the foundations of cryptography, so I thought I might as well mention quasi-Nizic arguments. And even, yeah. Okay, so what's the thing? What do we need to prove? We need to prove many linear relations. So specifically, what you want to prove when you're doing the growth 16, when you want to do the R1CS, you want to prove all these linear relations, okay? You want to prove there exists a single value Z such that ABC is on this form, okay? First thing you do is like, okay, this is an even only if. It's, again, you've done nothing here. It's just mapping polynomials to vectors. So you're writing this as proving that membership, that some polynomials are in a certain space of polynomials. So you have a matrix of polynomials, you have a vector of polynomials, and you're trying to say there exists a value Z such that ABC is a linear combination of Z, okay? In reality, this is not what we will be proving again, right? Because you never send polynomials, you send polynomials evaluated at a point, this is actually the case, is a commitment. So in reality, in the compiled protocol, what we will be proving will be this. We'll be proving that this polynomial, so the polynomial evaluated at tau embedded in the curve, the polynomial, so B evaluated in the trapdoor embedded in the curve, and C, and the same for C, is in this matrix, okay? So usually people think of this as a membership in linear spaces, but you already see that maybe the first problem here which is actually, there's actually no membership here because this is like a matrix that has many more columns than row, right? So like membership is trivial. Again, we are talking about a proof of knowledge. So we want a proof of knowledge that these vectors are in the space spanned by this.
Why did you say U1 rather than A1? Why did you rename A?
Because of tradition of grade 60.
Tradition.
No, of grade 60.
Yeah.
So, yeah. Okay, so even older stuff, right? For those really nostalgic. And we have the hash proof system. So I thought it's a workshop again for the foundations of cryptology. So let's talk a second about hash proof systems. So I'm using this notation because here it would be a mess. So I'm just saying a bracket notation for meaning A embedded in the curve, okay? What is a hash proof system? Well, it's a designated verifier proof system, okay? We have that the verifier is not a public entity. Not everybody can play the role of the verifier, okay? The verifier has chosen some vector K, and this is his secret key. And only the person that has the secret key can verify the proof. Okay, so there are like some public parameters, which are the statement. So the statements that we want to prove is we want to prove that this vector of group elements is in the image of some message M. Okay. So, and then there are some public parameters, and essentially there is the M that defines the statement, and there's also like a projection of M. Okay. So this is computed by the verifier. So you can think of it of some public key. Okay, the verifier chooses K and sends this to the prover. The prover now wants to show that this is true. What does he do? He uses this information to compute KTM times W. Okay? 1 second. Maybe let me show you first the completeness. Okay? First, why would this work? Well, the verifier is computing this information, and this is the same as, you just move the brackets, okay? This is the same as KT times MW, and this is the same as KT, there's a bracket, okay? So this works because actually the associativity of matrices. So what kind of, so just to make it more concrete, let's think of an example. So imagine you have that your matrix of group elements is just P and H, and your statement of membership is like you have 2 group elements, and you want to prove that Y is M times W. So which means that essentially you're proving that 2 values have the same discrete logarithm. Okay? So what would be this thing that the verifier, the key that verifier would be computing is just KT times M, so K1P plus K2H, and what is the proof is just this witness. Okay? Okay, what I'm interested about this is like the soundness. So the main idea for soundness is that if you have something that is not in the image, this information, the proof that the prover has to compute, is information theoretically here. Why? So the idea is the prover only sees the projections of the columns, no? It sees. You can see it in the example, it sees only the key times this column, okay? If you see the projection on a space, you have no idea of what happens outside the space. You don't know anything about what is KT on another space, okay? So these kind of proof systems, they have this information theoretic notion of security. And the other point is that, and as maybe trivial remark is that actually, and the security works because this is designated verifier, right? The moment the prover knows K, this argument that the verifier doesn't know the projection of Y in another set doesn't make any sense, right? Okay. Okay, so.
Is there some connection to the reduction for the Peterson commitment you showed at the beginning? In the sense that it's hidden.
Maybe. Actually, it could be, but now I can.
I think I missed this, but why is this called a hash proof system?
I don't know. Maybe
I think you can view the projection as a hash.
because it's compressing the
The matrix is random, right?
no.
No.
A
A
is
is
random.
okay.
Oh, okay, then you.
Okay, but anyway, the argument is, the point is that, okay, we have this hash proof system. The idea is you cannot, the reason why this works is because you cannot compute the projection on another value. Okay, now, there is a way, but this is like by definition, designated verifier.
So
Wasn't
this
it-
projection, you mean the projection of K?
K
on
times,
matrix,
well, I
right?
think of it as a projection
Linear
because you're giving the inner product, so of K with the columns. Okay. I don't want to go into this, but too much, but like the point is that the quasi-NISIC proof systems are sort of like a compilation of these hash proof systems into the public key setting, okay? You can make this publicly verifiable if you have a pairing, okay? Under different types of assumptions, I don't, I will skip that because it would get too complicated, but the point is that we have some analog computation and analog for security now. What we're saying is that unless the prover knows a witness such that Y is MW, it still doesn't know how to compute the proof. So the idea is, before we had this notion of like, if you give me something that's linearly independent, you cannot compute it information theoretically. Now we change it for, if you give me something that is computationally linearly independent, so that you don't know the witness, you don't know how to compute the proof, okay? So, and this is how in grade 16 they prove, sorry, don't know where I am. This is how they prove linear relations in grade 16, okay? So you want to prove this thing, which actually you have no chance, it's not really a proof of membership, you have no chance of proving this, because this is like, this matrix is too long, but you still have this notion of that computationally, you don't know how to compute a projection on things that look randomly linear independent to you, okay? So if you look at grade 16, you will see that there's like these kind of things on the SRS, and this is related to this, to how they prove the process. The point that I'm interested in making is that security relies crucially on the fact that it's not possible to reuse this key, okay? To calculate the projection on another vector that's not on the space. This means that this key cannot be reused across for another R1CS system. Okay, it's because then you would be giving too many projections of this, security is completely ruined. Does this point make sense? Okay, so imagine so the idea is if I change the matrix, I will be, and I use the same key, I will be using the same key for a different matrices, I will be giving away too much information for the key. Okay, so at this point I can prove anything. Okay,
K is beta, alpha.
I'm trying to use grade 16 and maybe it's not the best. But the
Yeah.
point is this, that you cannot reuse for when the key that you're using for linear relations, you cannot reuse it for another. And if you do that, immediately you can actually find an attack. Okay. So what are the consequences? So summary is like, okay, grade 16, the setup looks like this, okay? And this comes from proving linear relations like that. What you have to remember is that the prover cost has a few multi-exponentiations of this size, okay? And then it also needs, unfortunately, to compute Fourier transforms, okay? Why does it need to compute Fourier transforms? I like Fourier transforms, it's not personal. But the thing is that why do we need to compute Fourier transforms? Because when we're trying to prove that something is divisible, we need to do multiplications of polynomials and so on, okay? So this is the kind of So this is, you need to do these very, very large Fourier transforms, and this is where you get these quasi-linear factors, okay? Because Fourier transforms give you this log factor, these are field operations, okay? This you have linear in the number of multiplication gates for group operations, and quasi-linear in field operations because are all the operations the prover needs to do to compute these polynomials. The really cool thing is that it has 3 group elements, which means it's independent of the circuit size. And if you think about this, it's like mind-blowing, right? Like you have like 3 group elements and you prove any computation that you want. Well, for me, it is still mind-blowing. Okay, and the really bad thing, which is related to what I told you, is that the trusted setup is inherently circuit dependent because of the reason I told you. As soon as you reuse the key for another circuit, you completely break summers. And I'm not what time.
Same, probably have 10. We started fast. Yeah, 10 minutes. Yeah, you're in time.
Okay. Good. So, what does this? Why is this so bad? Like, is it really bad? This that the trusted set that is inherently circuit dependent. Well, as people who work in the area know that this is actually something quite bad. Why? Well, let's talk for a minute about trusted setups. This is like a famous image from the Zcash, like the first time they generated the parameters they needed for their system. And well, the founder was like destroying the laptop to make sure nobody knew, that the trapdoor, like it was a multi-party ceremony. Yes.
Okay, someone was raised.
Oh, okay. So, because it's really essential that the trapdoor in a SNARK is not known. If you know the trapdoor is like, if you know, for instance, this key for linear relations, you can cheat on the linear relation, but also if you know the other trapdoor that defines the polynomial, like the idea is you're checking polynomial relations in one point. As soon as you know this point in the field, you can make everything coincide so that really everything gets satisfied, right? So the thing is that generating these parameters is like a costly and complicated process for many reasons. First, I don't know if you have this saying in English, but the point is that first is that there's also like some communication is, right? Like you really have to convince everybody that this was like generated properly. Otherwise, nobody will trust your system knowing that maybe this was not done correctly. So it means also many people have to participate. If you use traditional MPC protocols, this means people have to be online, right? During the whole protocol and so on. So it's like a costly and complicated process. This is something that you don't want to do a lot, right? In particular, you don't want to do it every time you update your circuit, which is like the problem. And the topic of trusted setups is actually quite interesting. Marcus did some work here. So at least one thing that they did to improve the cost of the ceremonies is move from this multi-party computation model where parties have to be online and exchange messages to this updatable model where people do their contribution and then they can disconnect and then somebody else can come. And where here it suffices that one party in the process was honest, and then you get an SRS that is correct. Growth 16 was like immediately received quite some attention because it was like a very, very, like the previous one was Pinocchio, or there was also, well, no, but there was this, well,
Yeah.
anyway, it was like quite an improvement. So people were implementing it, and they were also like designing specific ceremonies on how to do this this setup. There is this protocol, the powers of tau, where actually what they showed is that you can generate the parameters of growth 16 in 2 phases that are updatable. Why not? sorry. And two phases that are updatable, okay? So first, essentially, you generate the powers of tau, and then you generate everything else that you need. So at least it eases the cost, but still, this is something that's not really nice. Like every time that you change your circuit, you have to change your setup. So this is why people started moving to universal and updatable SNARKs. So these are SNARKs that are updatable, but in a single phase. So you generate all this. So essentially, in the first phase, you just generate the powers of tau. And then there is a second pre-processing phase where you generate parameters specific to your circuit. But what is essential is that the second pre-processing phase is not trusted. So everybody can do it. So it's really a pre-processing and not another setup as in the original paper. Okay, and then the second thing is that these are universal. So it means that the part that is trusted, the thing that you generate is good for any circuit of a certain size. And this again is an example of what I said in the beginning, okay? The constructions that we have for universal and updatable SNARKs, as I mentioned, for instance, Plonk and Marlin, they have worse proofs. So they have larger proof size, not very much larger, they're still constant, but they quite a few, some extra group elements, but people are willing to make to accept this kind of blow up in the proof size because the setup is really something that's quite annoying for CRUD 16. Okay. Okay. So last step, 5 minutes. Okay. So last minute, I just want to give you an indication on, so this was how you prove linear relation in CRUD 16. This was determining how the setup runs and also determines like the main performance. And the same thing happens for Marlin. Okay, Marlin has another strategy for proving linear relations, and the main idea is that instead of proving, so what you would like to do is you would like to check all these linear relations, and what you do is like you reduce this probabilistically to checking a single linear relation.
But there's a question online about the over time complexity of course 16. Is it O of n or O of n log n?
It is O of n in group operations, O log n log n field operations because of the Fourier transforms. Okay, this is why everybody talks about avoiding Fourier transforms, right? It's like this topic of research of getting optimal size, optimal time provers. Okay, so, well, this seems like a really good idea because the verifier, so this is like an inner product relation, and the verifier could compute himself this randomized version of M, right? To check this relation. What's the problem? Well, the verifier can do that. There's nothing hidden, but this is way too large for a verifier that has to be succinct. Okay, remember that the matrices we're talking about, they have the number of rows they have is related to the number of gates. So really the verifier cannot check on its own that RT times M is correctly formed. Okay, so the prover needs to show that this is correct itself. So this introduces an overhead in the protocol. Okay, first in Marlin, this means to start with that you cannot have, it's not a fully non-interactive protocol like in CRUD 16 because you need some input from the verifier, which is this error, because you're randomizing the relation you want to check. And second, we still need to figure out how to prove this thing. Okay, how to prove that this is correct. I think I'll skip this. So the idea is that you can encode. If you have a matrix, you can encode it as a bivariate polynomial. Okay, and then if you do a partial evaluation of this polynomial, what you get is like a vector that's a row vector that's like sufficiently random in the space of the matrix. Okay, so the problem that I want to solve, which is I want to prove that a certain vector is sufficiently random and in the row space of the matrix, becomes a problem of really showing that some polynomial has the right shape, okay? Yeah, and this is like, this is actually too complicated, but the idea I want, because I have 2 minutes, but the important idea to keep from here is that you want to prove that this is a correct polynomial, this is a correct randomized vector. So it's the encoding of a randomized vector on the row space of the matrix. The important thing to remember is that actually if we were naive about trying to prove that this is correctly formed, we could commit to the whole matrix and later somehow open it to prove to the at a random point to prove that this is correct. But if we are naive about this, we will get something that is quadratic. Okay, the intuition is matrices like are something that is quadratic. Quadratic is no go, right? Like 2 to the 20 times 2 to the 20s, 2 to the 40 group elements. No, thank you. Okay, so the important things to remember is that there is a way that's called a sparse encoding. Okay, and this is like a common technique. So the question, so the main point is try to leverage the sparsity of this matrix, because most of the entries are 0, to try to get a protocol that allows me to show that this is a correct polynomial. Okay, and this is a technique that comes from Marlin. You're writing the polynomial as, you're writing this as a function of three values, the row, the column, and the value. That doesn't matter, okay? But remember, the main idea is sparse encoding. You have to learn how to use sparse encoding. Okay, so that's it. Conclusion, okay? Again, I think it's a nice way to present SNARKs by focusing on the linear techniques, because this actually highlight, like, I think it's a good orientation to understand where does performance come from? Okay, so here we have seen that the prover, I got tired of linear quasi-linear, so let's say O tilde is quasi-linear. So so we have that growth 16 has this problem that is not universal and you need a trusted setup. So this is like something quite bad, maybe for specific uses not so bad. And you have that the running time is this because of the Fourier transform. And y depends only on the multiplicative gates, because this is the size of the matrix that you need. For Plonk, I didn't have time to talk about it, but the point is that Plonk cannot really use R1CS. Why can Plonk not use R1CS? Well, because in R1CS, the matrices that you get are not permutations. Okay, so this is why Plonk first moved to another arithmetization. Actually, at the end, it was great, because then these other arithmetization like also show different ways of doing things. They introduce something called custom gates. So they have a way to more efficiently maybe arithmetize things, okay? But the underlying, so my understanding of Plonk is that the real problem was how to solve prove the linear relations. And for this, they had to move to permutation-based stuff. Finally, well, I put Spartan here, but just because it's like a similar thing, but based on multivariate polynomials, but feel free to ignore. But anyway, this is yeah, sorry, I wanted one thing is that because Plonk has to move away from R1CS, they need to get and write everything as permutations. They get a prover that depends on the total number of gates, including additive gates. Okay, so they don't no longer get additive gates for free. I multiply additive gates for free. Marlin that uses this technique, at the end of the day, when they have to prove that this is correctly formed, the performance that they get depends on the sparsity of the matrix. Okay, so in some sense, like this means that you no longer get here additive gates for free, right? Because somehow the matrix absorbs the additive gates. So at the end of the day, you have that one thing that growth 16 has that nobody else can have of this, the proof systems that use the other techniques, is that additive gates are for free. And that's it.